Today we're just going to share some SDN research that is synergistic with some of Kretzy's and SDN research efforts and provide information that would be of interest to the Kretzy research group. So thank you for being willing to share this information with us, and I'll turn it over to you.
Thank you. So work. So this is like it was mentioned. It is synergistic to the work that Kretzy does. So I thought I'd talk about it. And it's primarily the talk is around the tool. I'll be talking about the tool later on in the talk, but feel free to stop me at any point in the in the talk, or pause. We can take questions if something is not clear. We can go through it before we proceed further. All right. So there are two key motivations for this talk. One is there's security motivation, and then there's the resilience motivation. The security motivation is that we keep seeing these attacks, and they seem to be getting worse and worse on the power grid and other critical infrastructure systems. So we should have better design tools for these kind of networks, so that when we are designing these networks, we ensure there is some kind of guarantees put into the network that some things will act as you would expect them to act once they're put in production. The second is the resiliency guarantee, and this is a very famous, you probably have seen this event cited in a lot of talks. But basically, power grid and other critical infrastructure system has this unique property that failures can cascade through the system. So, for example, if you have a failure in the power network, it can actually affect your cyber elements, which can affect more power side, and so on and so forth and so forth. So people have done studies about this where you have the events, they seem to be the failures are cascaded. So again, this talk is primarily about cyber network. So we're not going to be talking much about the power side. And this talk kind of applies generally to all kinds of critical infrastructure systems as well. But the idea here is that, again, you want to make sure that there are some guarantees in place about when failures happen, they will be rectified correctly. So let's see. So when we talk about security, one of the main elements of security is access control. So you want to basically make sure that within this is an example from a substation network. There are 4 switches in this network. There's all kinds of elements that you would find in the power grid attached to these. And this is your big bad internet, right? So these things the configurations for these kind of networks are actually audited. There's an entity called NERC, which requires these networks to be audited, and there's all kinds of rules about this thing called electronic security perimeter, where what they require to ensure is that there's only so many things can come in from the outside to the inside network. So basically, you have like some kind of a wall, and in a typical power grid network, this thing would probably be a firewall. So this, I'm drawing this as a switch. It will become clear why the general one as a switch. But this will be a firewall, which will be blocking all kind of traffic going in from the internet and out to the internet. So you have some kind of protection. And this is a very key basic security requirement, right? But what we've often found that happens is during these audits is people don't have a good, understanding of what goes in and out of their network. I mean, there are firewall rules, but you apply them on a single device. Sometimes they're left there forever, and people forget about what was put in there, and then nobody wants to touch those things. So what you want is, again, you want to take the configuration of the whole network and say something about the whole network. Like, okay, what gets in, what gets out, and validate that with some kind of specification about what the world ought to look like, and then say, well, you have probably some violations or not. Similarly, consider the case of a network link or a device failing inside a power grid network or any critical infrastructure network. I keep using some power grid because it's easy to motivate, but any critical infrastructure network. And so we have this new paradigm shift which is happening in data center networking, which is called software-defined networking. It's really a glorified way of saying, well, finally now we can program our network. Now we can control our network. We can control our network devices with the standard API. That's basically the gist of it. There's a few other things that tie with it, but that's basically the gist of it. That hasn't been possible historically, but with new devices that's become possible, right? We have greater control, greater flexibility. But basically what typically happens is in an SDN setting, what you would do is, I'll go in more detail about this, but basically, if you want your control plane to react to failures, it will take some time. So if a link fails, for example, even currently in the internet, if a link fails, there's some kind of convergence time that goes around, and routers need to talk to each other and be like, okay, this is the new route now, and everybody agrees to it, and then new route is used. Same applies in SDN as well. If a link fails, the switch needs to tell this to the controller needs to respond with new routes, and same thing needs to happen. But the problem is that in critical infrastructure networks, you don't have the luxury. The applications don't have the luxury to wait around for that kind of thing to happen because they require very short convergence times. They can't tolerate really large amount of packet losses. So what they are looking for is what I'm terming seamless resilience, and I'll be talking. So when I say resilience, I'm talking about continuous flow of data, even when that links or devices are failing, so that the interruption cost is very minimal. By minimal, I'm talking about you recover from that fault within a millisecond or a few milliseconds, and you don't lose many packets. That's the order that we're talking about. And there is this mechanism which has become recently, it's kind of seeing an upsurgence, but it's been around in networks. It used to be called fast reroute in MPLS world. Now it's called fast failover in SDN lingo. But really, the idea is that you have this switch which makes a local decision. So you can't tell the controller what the new routing is going to be, but the switch will make a local decision as soon as it detects the link has failed. And now, if it makes a local decision, bad things can happen because, of course, now the traffic needs to take some other route. It may or may not take the right route. That's the problem, right? So here's a little illustration. So again, this is a very simple ring topology. So I'm trying to get this traffic out from this SCADA controller to this Ethernet relay out here. And this is my primary route, right? Everything is working, nothing fails, this is my route. Suppose this link fails, what will a good fast failover scheme do? It will take this route and deliver the traffic, right? Something else can happen, which is, well, instead of that first link, the second link fails. And now the traffic kind of needs to turn around and go around the ring and be delivered to the relay. And all of this is happening without any control plane intervention. Your controller is not getting involved. So the devices really need to make a very, very carefully designed, correct local decision. Hence the problem, which we are trying, and we need to validate whether the devices are actually going to do that. So that's basically the two key reasons why this tool that I'm going to be talking about has been built. It's going to validate whether it's meeting security, and simultaneously it's going to validate that it's also going to meet its resiliency requirements, which are expressed in some way. We'll talk about how they're expressed. So this is a short primer on software-defined networking. What you have is a controller, you have switches talking to the controller using a secure channel, there's a northbound API, and you have an application sitting on top of that northbound API. This is where our tool sits right now. So the tool can look at the entire network configuration, so all the switch states, the topology, what it currently looks like, it is there. It can store logs and whatnot, and it can perform some analysis, which is what this tool does. Particularly what you need to do is you need to take into account what a switch is capable of doing, and then exhaustively validate all the states in which the network can be in. This is exhaustive validation. And it can be, it can be computationally extensive. So there are ways you could, so basically that's where the contribution of this work is, that there are ways in which you want to cut down the amount of validation that is going on. So again, you have control plane state, and you have a network-wide policy. This policy is basically the designer or the operator saying, well, I want this thing to happen, and I don't want that thing to happen. That's just, and it's expressed in some manner. Let's just call it, we'll go into how we suggest it should be expressed, but right now, just consider it as, there's some way, some language, it's expressed in that. Then you have to do some static validation, and then you have to detect policy violation. And this is all happening at design time. This is not happening during runtime. You design your network. Before you put it in commission, you go through this process. And if there are any violations, you rectify those, and then you come back at it. That's the idea. So in the rest of the talk, I'll be talking about what happens to the packet inside the switch. Then I'll be talking about this, how do you express policies, which can, talk about these kind of requirements. We'll talk about the model for the network. We'll just talk about the design of the approach. We'll evaluate, and we'll conclude. So far, so good? Right. So this is a typical OpenFlow 1.3 switch. It is part of the spec, basically. I'm not putting the whole spec here, but the relevant parts only. So a switch, these kind of switches, they have multiple tables inside them, and each table has a bunch of flow rules, right? And there are flow rules. These flow rules, what they do is they have a match part, which basically is like, if you've ever written an actual rule, it's like, match on this port, this IP, this MAC address. Match is just a description of traffic, which you're talking about in that rule. Instructions are what would you like to do to that packet. So these rules, they are installed by the application, which again sits on top of the northbound API, or sometimes even the user can just go in directly and install these kind of rules, right? So this is what's happening during design time. This is what people are putting inside the network. This is what we are going to validate. So these instructions, they can come in many forms, but two key forms that we are interested in for the purpose of this talk is you could send the packet out to some port. You can say, hey, I want this packet to be sent out this port. Or you can say, well, you can give it a list of ports. You can say, if this port is active, please send it out here. But if that fails, detect that immediately and send it out here. But if that fails, send it out here, and yada, yada, yada. Besides those two key things, there are other things that these switches are also capable of. Since there are multiple tables here, they can modify packets from table to table to table. So they can modify a field, some table, there will be a table in the switch which will be like slapping a VLAN tag on the packet. Or there will be a rule there which will be popping out the VLAN tag. It will be removing the VLAN tag. Or something will be modifying the MAC address. There's all kind of arbitrary operations that are going on here. Not arbitrary, I shouldn't say arbitrary, but like a huge variety of operations that are going on here. But these are the key operations that we'll be talking about for the purpose of this talk. But the reason I'm mentioning these other things is because the model needs to capture them. Like because that's what your ultimate behavior of the network will be depending upon. So let's talk about how you would express requirements of a network. Okay, so this is the policy spec. And this policy spec basically comprises of different elements. What you have to do is you have to describe places of interest to you. And in these networks, they are small enough for people to kind of know which ports exist in the network, and you can kind of say, okay, these are all the ports that belong to this zone. The reason they call it a zone, there are historic reasons for using that term because people already use it in some configuration lingo. But the idea is this is just a section of your network. That's a zone, right? It's just a set of ports. We call it a zone. Traffic set is just like the match field in the flow rule. Essentially, it's a description of what traffic that you are concerned about. So you're describing a policy, and you're describing what traffic would you like to talk about. That's just a traffic set. That's what we decide to call it. Failure events, these are the contingency events that you are concerned about. So you're concerned about a certain set of links that may fail, or you're concerned about a particular network device that might fail. So those are the events that you need to describe in that policy. And then you have constraints. These are the things that you actually really, really care about. You want connectivity to be maintained. You want to make sure something cannot talk to the other thing, so you put an isolation constraint on it. You want to make sure that the paths have a certain length so that, traffic can meet certain requirements like a timing requirement on it. And you want, sometimes there are requirements like you want to avoid a link. You want to make sure that a path for, say, internet traffic does not go through a link. So this is all talking about in abstract. Let's go and look at a very specific example. Now this slide is a little busy, so I'll go through this step by step. Again, this is the substation network we were looking at earlier. And so you have three zones that, this would ideally be done using a UI, the nice UI which will be defining these things. But essentially you have three zones in this network. And, and those zones are concerned with this relay. One zone is capturing the relay, the other zone is capturing the internet. The third zone is capturing real-time automation controller, RTAC. Actually, so 2 and 3 actually are clubbed together. So there's Z2, which is capturing both this IED and this relay. So both of them belong to the same zone. And what this policy is trying to specify is that you want this ESR and this IED to be connected to the RTAC even when any single link in this topology fails. So if any link fails, I still want that connectivity to be established. Like I don't want, and it can be done because you have all these redundant links in here. So you want the routing to have that property. That's what this first element of the policy is trying to capture. Right, and the other thing that you are also wanting to make sure is that when you do take alternative paths, you don't want the path to go around in a loop. You actually want to make sure that there are no more than 3 switches in that path. So those are the 2 constraints expressed in this particular constraint set here. And so yeah, and the event here is a single link failure of any given link. So basically this is just writing, there's all these links which are just written out one by one. And that's one of the statements. So you compose this statement using the zone. So these are this is your source zone, this is your destination zone, this is the traffic that you're concerned about, and this in this case is the wildcard traffic. You want this to apply to all traffic, and you have some constraints, these are the events that you care about. So far so good? Are there any questions in the slide? I understand the slide is a bit busy, so.
Can you say something about the constraints?
Yeah, so there are 2 constraints in this statement. There is a constraint called C. So I was talking about all these 4 types of constraints that there can be. So there's the connectivity constraint that we are using here, and we are using L3, which is the length of the path, which I don't want it to exceed more than 3 switches. Those are the 2 constraints we are using here.
Okay.
Okay. So the second rule here is I want the path of HTTPS traffic from the internet to RTAC to not cross this link between switch 3 and switch 4, right? Whatever reason. So again, so I'll take the zone which represents internet. I'll slap that as my source in the next statement, and Z1 is my zone which represents this RTAC. And now the traffic field, because I'm only concerned about HTTPS traffic, I will modify a field in my traffic set to express that. And that's that. I mean, and I don't really worry about any failure events in the second statement, in the second requirement, right? So the event set for that statement is empty. And then I've composed my policy, I hand it to the tool to validate. That's that. Okay. So now, like I was saying, I need to model the network, which contains all these flows, it has a bunch of switches in it. And the way I model it is, the model needs to have 3 broad properties. It needs to be very efficient. You can't have a model which represents all the infinite number of states that exist. So you have to be careful about how you model it. you have to model it so that it's composable, meaning you can talk about network as pieces. You don't want to be in a situation where you model the whole thing all at the same time. You want to be able to decompose it. You want to maybe build a tool which can model this in pieces and one at a time, one switch at a time, or one part of the network at a time. And the third thing is it needs to explicitly represent traffic, because we care about what traffic goes from this point to the other point of the network. The model needs to capture that element. So the model that we are proposing in this work is called the port graph. And again, so you take the state of the SDN and you model it as a directed graph. And nodes in this model are any places of interest, right? So what are the places of interest? So for physical ports, you have ingress and egress nodes. And you also have nodes representing each table in every switch in your topology. The reason you have that is because tables can actually modify things. So there are interesting things happen in this network on tables. So you need to model those as first-class entities in this thing. And the edges represent the transfer of traffic. So from an ingress port node, some traffic goes to some table, and from table it goes to another table, and the traffic goes from that table to some egress node. So when there is an edge, that edge models the transfer of traffic. That this traffic can go from this place to the other. And each edge has a filter, and the filter is basically, again, another match. It's like saying this is what the edge will pass, and everything else will not pass. And it also captures modifications, and this is where it kind of gets a little gnarly. I mean, you have to capture if the traffic is being modified at the predecessor of the edge before it is sent out to the successor. So this is your model so you have your network, you have all your tables, all the ports, you build a graph, it's a directed graph, you read through your rules, you construct this graph out of that. There is another model, so this is the part where I was talking about the explicit representation of traffic, and we just call it admissible traffic set, ATS. The idea here is that, so now you have this graph, right? And what you want to capture is, you don't want to capture what happens from edge to the edge. What you really care about is what goes from any given node in the network to any other node in the network, right? If you knew that about the network, then you can validate all kind of policies using that, right? And that's what ATS is. It's just what traffic is being admitted at any node P to any other node D in the port graph. And then there's this thing called T that basically is, any node has a bunch of ways it can go, bunch of places, bunch of successors, which are allowing some of the traffic it is admitting. So, for example, a node is admitting part of its traffic through one table, part of its traffic is being admitted by some other table. T is just what is being admitted by any given one successor. And if you union all of them, you get the whole group. That's what T is. But the T itself is defined by whatever the successor of that edge, the successor that you have of that node, is admitting from that point, and you intersect with the edge filter, and you get T. So, and this is a relationship that holds true. It's a useful relationship. It comes in handy when you're trying to model this. And one key part about this model is that you can do incremental analysis, meaning if you changed things in the network ever so little, meaning you maybe added a rule or some link failed, you want to do some kind of contingency analysis, you don't have to do everything from scratch. You don't want to be in a situation where you have done this exhaustive modeling and little thing changes and you do everything from scratch. And in this model, you can perform incremental analysis like that by comparing. So if ATS prime is something that happens, if ATS prime is the traffic after that event has happened, you compare that with the set that was before the event, and if that event, both the sets are same, you can say that that change didn't cause any, any changes to my admitted traffic, or it did, and then you have an algorithm which takes care of how to propagate that change. So these are two key elements of the model. There's a graph and there's a ATS, there's a traffic set, ATS, admitted traffic set, which is capturing what goes from one node to the other node in that graph. So how do you do this? So that I was just talking about the model in abstract, but what you really do is you first construct a bunch of port graphs. You construct a port graph for each switch. So you first go and try to capture what each switch is capable of doing. Then you construct a graph for the whole network. And then you compute ADSP using a depth-first search through that graph, through all those graphs. And then this is a key point again because we want to validate resiliency. This is just to say you put a little flag on edges which are not active, meaning they are just there when failures happen so that you can look at them and sort of capture their effect when failures do happen. So that's just saying that there's a flag there. So let's look at how would you translate a network topology into its constituent port graph. So this thing is trying to send some traffic. So you have the switch S1, it has two tables. You have switch S3, it has two tables. When things arrive at table 0 from port 1, what the switch does is it sets the VLAN ID to 3 and sends the packet to the next table. And then there is a match there for VLAN ID 3 conveniently, and then you make a decision. If the port number 3 is active, you send the traffic out port 3. If that's not true, then you send the traffic out port 2. That's all that's going on. So this is what's happening at this switch, and this switch S1 is connected to this switch S2, and you have another switch S3 here. So port 2 is where the switch S1 connects to S2, and port 3 is where it connects to S3. So basically, all you're really just trying to decide is when the traffic does come from this host, where should it go? Should it go to port number 3, meaning S3, or should it go to port number 2, meaning S2? That's what you're trying to decide.
Excuse me?
Yeah.
What is going to happen if the link between S1T0 to S1T1 is? Because you said in previous time that whatever link happens, we should maintain the connection.
Right. So this link cannot fail because it's inside a switch.
Okay.
This is a link between. This is a directed edge between a node that represents table 0 and node that represents table 1 inside the switch. So this link cannot fail. I'll talk about what links can fail. So the links that will connect the switch to other things, right? I mean, at least, unless the IC breaks down and then everything will fail. But we're assuming that within the switch, things like this won't happen. And so you model these two things using their corresponding port graphs, and this is the model for the entire network. And in this graph, you don't represent the ports that are connected to the host directly. So now this is where that link is. So this S1E3, this is that link. This link that connects S1 to S3, that link can fail, right? So when this highlighted link fails, what would happen is you have this link becoming active. Sorry, this link becoming active, right? So, okay, so I talked about what these graphs look like, how would you construct them, what their structure is. This is an illustration of what actually happens in the depth-first search. So you start with all wildcards, okay? And you basically progressively run a depth-first search. And as this traffic reaches other ports that are of interest to you, the traffic becomes more and more specific. And it starts because there are all kinds of flows that will be affecting that traffic. So, and you stop at all nodes that are connected to the host, or all nodes that you cared about in your policy stack. So basically, yeah, so I just wanted to show you that the data structures that represent these things, they become gnarly and gnarly and gnarly as the search goes deeper and deeper and deeper. So basically, the rest of the talk is basically evaluating this in different settings. So what we did was we did the evaluation entirely in a software environment. We didn't have hardware switches where we could, or that many hardware switches for doing some kind of scaling experiment. So we used Mininet and Ryu. There was 16 GB of RAM on the machine where we were, doing this, and we were using 2 processor cores. And we were doing these analysis, the policy validation analysis, 10 times. So, and we were plotting how much time does it take, right? That was the key metric of interest to us. So first there's a MicroBenchmark, and this MicroBenchmark is, the key reason for doing this was to say, does doing incremental analysis using this model, is it actually useful? Does it actually help with anything, right? So what we did was we took a bunch of different topologies, with varying number of switches in them, and what we did was we added more and more hosts to those topologies. So on the x-axis on both of these plots, you have number of host pairs that are in a given topology, and on y-axis, it is basically how much time it took to perform certain computation. And we're plotting numbers for pre-computation, and when we make a little change. And the change here we are making is we fail a link, and we ask it to recompute the effect of failure of any given link. And we of course put flows in these topologies, and as more hosts were added to the topologies, you had more and more flows being added. And the flows had a property. We ensured that these flows would always provide a single link failover. So you can do that, well, in all but this topology you could do that. Because in parts of this topology are such that you only have a single link connecting some part of the topology. But wherever it was possible, we were providing failover. And we had a policy which was requiring that the path length be less than the diameter of the network. So take the longest path on the network, and we wanted the resulting path to be less than that. Now, the pre-computation time, like this is the time it takes to construct the initial port graph, that goes up really fast. So in some cases it was taking us 10,000 seconds, which is a couple of hours for topology which had 6,400 host pairs. But what we were trying really was to see how long does it take to see what is my currently active path. If I knew what my currently active path is after the single link failure, I would be able to answer this question, right? Whether the length of the path is smaller than my threshold. And that number was taking, in the worst case, it took us 2.5 seconds, and that's a huge gain. So what we're saying here is basically the big result of this plot is that, yes, it is useful to use this model, and it really, really helps incremental computation. And you can quickly simulate a lot of different scenarios, failing a given link and recomputing the currently active path is super cheap comparing to doing this whole thing from scratch. Especially for some topologies where it could take up to hours. And by the way, all of this was being done really using a Python prototype, and it is only running on a single core. So there's a lot of parallelism gains that can be had in both of these computations. But the net effect of both of these results is that, yes, you do gain a whole lot, orders of magnitude of time, if you do incremental computation. Then we did a case study. This is a case study for validating resilience in a substation unit. This is the same plot I was showing, the same picture I was showing you earlier, except now we are adding a lot of hosts in this picture, right? So the policy is same. I still want those 2 policy statements that I was talking about earlier to be validated, but now I'm just adding a lot more hosts. To the point I'm adding, in some cases, I have 144,000 hosts in this topology, right? I just keep adding hosts to each one of these switches, right? Just to see how does this thing scale, right? Yes.
I mean, it's nice that you're looking at the scaling, but what do you think is a reasonable number of hosts to be within a substation?
So yeah, so host pairs is what I think. Yeah, so a reasonable number of hosts there's no straight answer to that question. If it's a large utility, you will find there's 100,000 host paths in a very small network. Like these numbers get like pretty fast. The other thing is
by substation network.
So the number of hosts is the square root of this number. That's one, which can be a much smaller number. This is the host pair, right? X-axis is the host pair. That's what you need to pass.
What do you mean by substation network? Do you mean a network within a substation?
Yeah.
It's definitely not going to be in that.
Yeah, it won't be this much.
Yeah.
It won't be that many, I would imagine. It would be much smaller than that. But this is a stand-in for any kind of critical infrastructure network, which looks more or less like an enterprise network. And you care about these kind of policies in the network. So yeah, then we just wanted to scale it up and see how far, especially how the curve kind of bends. And the idea here is, again, this picture is showing you that you do spend a lot of time doing the initial analysis, but since you're doing this bi-level graph decomposition where you're spending a bunch of time trying to validate what goes on in a switch, and you come back at it in the network-wide graph, that buys you a whole lot of gains again, even in the incremental computation. And beyond, so if you keep adding hosts, that doesn't really matter much. And that can be a concern. I mean, maybe 144,000 host pairs is a bit much, but 6,400 is probably not that many. All right. And this is a case study which shows using the tool in a microgrid setting. So microgrids, there's this, I should have cited that on the slide, but there's a lot of different ways people have proposed how you should be architecting and protecting your microgrid network, especially if they're connecting to some central point. And the idea is to use VLANs, and they call these things enclaves in functional domain. So enclave is basically a glorified name for a VLAN, and functional domain is basically you have all these nodes which are spread out, say, doing some kind of control operation, and they still need to talk to each other, but they should not be able to talk to anybody else, right? So they could be spread out across all the small grids, all the microgrids, and they call them a functional domain. But essentially, this network has about 20 VLANs in it, okay? And you have 19 switches here, and you have 6 microgrids, and you have these rings representing each microgrid. And again, the question is, how does this thing scale? So what we are changing here again on x-axis is how many hosts are there in an enclave, which would represent how many hosts are there in a microgrid, and we go up to 12. And there's a lot of enclaves here. And then what really happens is once you start representing this, you have more and more policy statements, and that's because you have to capture all possible relationships. So the number of statements grow as a square. So that's why this number starts growing more like a square term. But yeah, I mean, again, this is not something which is something that you cannot do. Like this is just 250 seconds. You should definitely do this before you put something in production, right?
So, Rakesh, I think in your something implicit in your assumption is that you're operating under the notion that any node is likely to communicate to any other node, which I think is perhaps an invalid assumption in the grid environment. It may be a worst case assumption, but in terms of common case, normally it's an aggregator that's talking to a host, and in some particular scenarios, you may see relay-to-relay, block signals, for instance, that would go across the network depending on the configuration. But that would be limited to not an n-squared notion, but a pairwise notion based on physical line topology, based on the number of buses that are there.
Right. So, but the square here is not really coming from having more or less hosts talking to each other. It's more of I have all these VLANs. I don't want any segment talking to any other segment.
Yeah, but
That's a larger
this
decomposition.
impacts your prior one too on the number of potential flows.
Yeah.
Like the 100,000 would
Right.
assume.
Not all of these hosts, not,
Yeah.
I totally, actually, so, yeah, you're right. Not all those flows would be enabled in an environment. Like, a lot of them actually would be blocked. You're right. Totally, yeah, because you don't want all that communication going on. But what I'm saying here is basically, even if you had all that communication going on, validating that is not something that is, like, it's not going to take too much time. It's like, you just have to spend 100 seconds to validate.
Sure.
Yeah. So if it's less flows, the chances of this analysis taking less time is actually higher. Like you'll take it less time to validate fewer things because there'll be fewer rules. If there are less flows, then yada. But yeah, this is trying to capture a worst case where you have everything talking to everything. Yeah.
That slide, I'm not convinced that the square function to be very linear.
No, so
you need more points on the.
Yeah, I should probably have more points, but yeah. So if you look at the stop number, it kind of goes.
I'm simply a straight line.
Okay, all right. I mean, I looked at the numbers, but yeah.
Yeah,
sure. Okay, yeah. I mean, it's a very slowly growing product. It's not linear. I mean, I tried to fit it, but anyway. So, but yeah, I mean, the idea here is that if it's going to take you 100 seconds to do this kind of analysis, you should totally do it. And before you put these things in production, this should be part of any design that is going to be used for power grid network. And this can help people to comply with their audits. This can help people to basically make sure that failure conditions are captured. And this tool is going to do this exhaustively for all different cases.
You're intending this as an offline analysis, though.
This is offline analysis. This is happening at design time. You put your flow rules in, and you say, okay, does this meet my requirements? Yes.
So, have you put any thought into how to obtain that initial data set to do the analysis of what the flows actually need to be? That's often not documented or determinable in any way.
Right. So, are you asking the question whether, so there are two questions here. One is how should you actually construct the flow? What should the routing look like? That's one. The other is how do you acquire the data? Which one are you asking?
I'm more asking the second one. The first is an engineering, which is subject to the principles of the system. But the second one, to do the analysis, if you're expecting a utility operator to run this, how would they get the data set by which they could run this analysis?
So this is being proposed for SDN. The idea here is that when you can take a snapshot of your network state, which is available oftentimes in your controller, and run this. That's the idea. So, and that snapshot can be taken at any point in time.
So you would assume an existing deployed SDN,
yes.
Not that a company is adopting SDN and putting it in place and wants to do this pre-engineering.
Right. So the workflow here would be, I'm going to put some rules in my network, which will meet some requirements. And you'll go and put those in, and you'll run this through after that. And you say, okay, if I do this, will I be okay? That's what this tool is doing. It's not, what it is not doing is, you tell it the requirement, and it goes and synthesizes the flow rules for you, which is the first thing I was telling. How do you construct these flow rules which have these properties that you're talking about? And that is actually a well-credited fact. Like, the reason I was able to validate these things is because I had to construct them, and there's a lot of literature around how you construct flow rules which have these properties, where they do failover. Like, that's a well-studied problem. But the validation problem is kind of new and exciting in some ways because it deals with the state space which explodes really fast. So yeah, basically to conclude, what is presented here is a framework for validating resiliency and security requirements for an SDN, and you're doing this by exhaustive packet flow analysis. We present some models and designs for data structures that should capture that model, and you can really do incremental computation on that model, and it provides huge gains, and you can scale to larger topologies. It won't scale to internet-size topologies yet, but it's going to scale to topologies which we currently think of or conceive of. I mean, I think in one case I I've tested this tool. I don't probably have numbers in there, but I have tested this against topologies with 49 switches with like 48 ports on each switch, which is pretty bulky. Like it, you know, I have yet to see those kind of things in the wild. I haven't come around. So yeah, is there any more questions? I'm happy to answer.
A reminder to our online audience to unmute yourself if you have questions.
Just a comment. I think that's a nice result that you got, that you can have pretty much a bound on the expense of this validation thing.
Yeah.
I think it's a good result.
Thanks. All right. Well, no questions. Everything was so clear. I'm not at all. All right.
All right, let's thank the speaker.